Hi all. Today I want to talk about hobbies. Every person has something that they like to do and get pleasure from it. One of my hobbies is moonshine. The process itself fascinates me. The result of this process is like a bonus for my work. The most important thing, in my opinion, in this process is the tool. The better the tool, the easier and faster the process, thereby getting the result faster. Today, in my opinion, mesh columns and their modification are the most popular. These are structurally uncomplicated devices that make it possible to obtain various types of products, for example, aromatic distillates or pure alcohols. It all depends on the desire of the user. But as personal experience shows, this type of tool is very difficult to make work stably. This instrument is very sensitive to external disturbing influences. A large number of solutions have been proposed to improve the operation of the Marsh column, and I was even ready to purchase these solutions, since I believe that it is easier to purchase something ready-made than to reinvent the wheel myself. But with a more detailed study of these solutions and the principle of their operation, I came to the conclusion that these solutions are not entirely suitable for the task that, in my opinion, should be solved to achieve stable operation of the Marsh column. Well, I bring to your attention my solution to improve the operation of the Marsh column. But before we grab an Arduino, a display, a temperature sensor, and write a program, let's first understand the theoretical part to understand what to take and what to control in order to stabilize the mesh column. I will not talk about the operating principle of the mesh column itself, about the transfer of masses with different boiling points. I propose to look at the solution for stabilizing the mesh column from this angle. And so I have a typical mesh column, and more than one. It consists of the column itself, which include a refrigerator and reflux condenser located in a special way, and all this together stands above the evaporation cube. In simple words, the operation of the system is to heat the evaporation cube and cool it using a refrigerator and reflux condenser. At the same time, in order for this system to remain stable, it is necessary to ensure equality between the supplied thermal energy and removed one. Let's write down the energy balance, where Q supply is the amount of the heat supplied to the system, measured in joule, and Q removed is the amount of the heat removed from the system. As we can see, if the expression is not equal, the system becomes unstable. It would seem that everything is simple. You just need to ensure the energy balance. But how can this thermal balance be implemented in practice? Let us consider in more detail how heat is removed from the system. It occurs with the help of a refrigerator, a reflux condenser, and heat losses from the surface of the system. Let's rewrite the heat balance, where Qref, amount of heat removed by the refrigerator, Qcon, amount of heat removed by the reflux condenser, and Qloss, amount of heat removed from the surface of the apparatus. As you can see, now the task has become more complicated. It is necessary to ensure stability in several components in the system, so that the energy balance is maintained. But again, it is not clear what to measure and what to control. Well, let's move on. As everyone understands, the distillation process takes some time. Let's introduce a time component in our heat balance and let it be in seconds. Let's divide the left and right side of the heat balance expression by the process time, and we get the following. From the school physics course, we know that energy is equal to power multiplied by time. Let's rewrite our heat balance. We get the following, where P supplied is the thermal power supplied to the system, measured in watts. P loss is the thermal power dissipated by the surface of the apparatus. Now let's look at the left side of our heat balance. We won't look at the right side for now. Since my evaporation cube is heated by electricity, the power supplied to it will be determined by electrical characteristics such as where U net rated mains voltage, I heating electric current flowing through the heating element. Ohm's law is also known to everyone from a school physics course. Let's write it down for our case, where I heater electrical resistance of the heating element. Substituting this expression into the expression for the supplied power, we get the following. As a result from the above expressions, we obtain the heat balance expression. I specifically left in the expression the parameter of the amount of the heat removed by the reflex condenser and refrigerator in order to further show what they are converted into, but that will come a little later. Well, let's take a closer look at the issue of power supplied to the evaporation cube. As is clear from our heat balance expression, we must somehow ensure that the power input remains constant regardless of external factors. Since we use AC electricity for heating, we will indicate its main parameters. This is the amplitude value and frequency of the network. The amplitude value is equal to the effective value. In our case, it is 2020 volts, multiplied by the root of 2. We also remember from the school physics course that the instantaneous value of the amplitude of the mains voltage over time is described by the sine law and has the following expression, where omega is the angular velocity associated with the frequency of the mains voltage. T observation time. Since we will consider one period, we will limit ourselves to a review time of 20 milliseconds. Let's build a graph of this expression. Basically, he doesn't tell us anything. Since we have a heater that has a certain resistance, in my case the resistance of the heater is 16 ohms, we can obtain an expression for the instantaneous current value through the expression for instantaneous voltage. It looks like this. Let's build a graph, but this also doesn't tell us anything. Well, let's now look at instantaneous power, which is equal to instantaneous voltage multiplied by instantaneous current, and graph it. But why am I doing this, you ask? But here why. Let's look at the instantaneous power at operating voltages of 190 voltage, 220 voltage, and 230 voltage. These are quite acceptable operating voltages for our networks. And what can we see? Fluctuation in mains voltage from 190 volts to 230 volts result in power fluctuation from 2270 watts to 3327 watts. That is a little more than 1 kilowatt. And mains voltage fluctuations from 220 volts to 230 volts lead to power fluctuation from 3044 watts to 3327 watts. that is a little more than 280 watts. Such power fluctuations, believe my bitter experience, greatly affect the stability of the mesh column. Well, from all of the above, it becomes clear that we need to somehow achieve constant heater power regardless of fluctuation in the mains voltage. Next, there will be a little higher mathematics, with the help of which we will obtain the dependence of the effective power on a certain alpha angle. This angle will determine how much real power we will get on the heating element if we use part of sinusoid. Many guessed that this was nothing more than a triac regulator. Let's plot the dependence of the effective power on the alpha angle, or the opening angle of the triac. As you can see, the dependence is not linear, but we can already work with this. Let's summarize. One of the factors in stabilize the mesh column is stabilizing the heating power. We also obtain the dependence of power on the opening angle of the triac. Now the question is, how to stabilize power? The answer to this question has long been given. We need to measure the current power of the heating element, compare it with the specified one, and if there is a difference, then reduce or increase the opening angle of the triac. It looks something like this. What does it look like? It's like a closed system, and where there is feedback, the theory of automatic control begins to work. I will also say that in reality the wattmeter does not produce values instantly, but with some delay associated with the physical measurement of power. The opening angle of the triac is also not physically established immediately, but with some delay. All this together leads to instability of the regulatory system or to its absence. Question: what to do? The so-called PID controller comes to the rescue. To put it simply, this is a regulator, the settings of which allow you to correctly control the object over the entire range of the controlled value. I'll make an emphasis. The PID controller is configured for a specific object. In our case, the control object is a heater plus a power meter and plus a triac control. And the controlled value is the power from 0 to the maximum value. And within this range, the regulator must stably maintain the set value. From the course of automatic control theory, it is known that the PID controller, in the general case, has the following expression, where YT, control action on the object of regulation, KP, PID controller gain, ET, control error, difference between the set value and the measured value of the controlled object, TI, integration time of the PID controller, TD, differentiation time of the PID controller. But since our system is digital, this type of PID controller is not suitable. Let's consider a discrete PID controller and consider it for the current sample. Let's call it N. And previous sample, let's call it n-1. For the current interval n, the controller will look like, where En, error value at the current time interval, En-1, error value in the previous interval, delta t, sampling time, and for the previous interval n-1, it will look like. As can be seen from the two expressions, the integral components contains an adder that accumulates the error from the moment the PID controller operates. It's not entirely convenient. Let's do this. Subtract the previous sample n-1 from the current sample n. Then we get the following. As you can see, we got rid of accumulation of errors, and now it is enough to have the error value of the current sample and the two previous samples. As you understand, with this action we received an increment in the control value per object. Then the final control value will look like this. Well, it seems that we have more or less figured out the stabilization of the regulated object. Now a new question. How to determine the parameters of the pitch controller for our controlled object? Let me remind you that a discrete pitch controller has four such parameters. This is Kp, the gain of the pitch controller, Ti, integration time of the pitch controller, Td, differentiation time of the pitch controller, delta T, sampling time. The sampling time depends mainly on how fast or inert the control object is. That is, if the regulated object is quite inert, then you should not often take samples of the measured value of the regulated object, and vice versa. But how to determine the other three parameters is another question that needs to be answered. There are essentially two ways to obtain these parameters. The first is manual tuning. There is an algorithm by which one or more parameters of this pitch controller are changed, and the reaction of the controlled object is observed. Based on its reaction, it is determined which parameter of the pitch controller needs to be changed, and again the reaction of the object is observed. In this iterative way, stable operation of the object is achieved throughout the entire control range. But this can be done by experienced people who have tuned more than one regulator in their professional activities. I'm not one of these people, therefore the second option remains for me. This is to get the pitch controller settings in automatic mode. There are quite a few options for auto-tuning the pitch controller, but everyone has the same principle. First, somehow obtain the characteristics of the control object, and then, based on these characteristics, the coefficients of the pitch controller are calculated. For me, this option is more acceptable, since when replacing the control object, in our case it is a heater, with a more or less powerful one, it will be enough to me to restart the auto-tuning to obtain new parameters of pitch controller. I use the method of moments as a pitch auto-tuning algorithm. It is well described in this document and is quite simply implemented on microcontroller. If anyone is interested, you can read it. Well, it seems that we have more or less figured out the theory of stabilizing the Marsh column. Now we can say a clear task. Develop a stabilized heating power regulator for the Marsh column. This will be the solution for the left side of our heat balance that we looked at above. A little later we will look at the solution for the right side of our heat balance. It will be a completely different device. We will look at the development and implementation of the stabilized power controller in the next video. See you later.